This is Donna Nelson at the University of Oklahoma, and I am recording a lecture for my Organic Chemistry 1 class, and we are on Chapter 1. This is Lecture 2 of Chapter 1, a review of general chemistry, electrons, bonds, and molecular properties. So you can see I've already recorded Lecture 1. This is Lecture 2, valence bond theory, molecular orbital theory, hybridized atomic orbitals, predicting molecular geometry, Vesper theory. So let's look at valence bond theory. A bond occurs when atomic orbitals overlap. One can have, an electron is like a wave, and so as you bring the two waves closer together, you can have either constructive interference or destructive interference. And you can think of this point at which the wave crosses the axis as a node. And so this corresponds very well to the bonding orbitals where there's constructive interference, and the anti-bonding orbitals where there will be nodes. So, as it says, only constructive interference results in a bond. This corresponds much more to an anti-bonding orbital. And so here you can see this would represent the bonding orbital for when one brings two s atomic orbitals together and they overlap. This is what the atomic orbitals look like. This depicts two atomic orbitals overlapping. You can see these are two spheres that have been brought close together. But this is an actual depiction of a molecular orbital. You can see these atomic orbitals are still localized. Each is localized around its own nucleus. But here, the molecular orbital is delocalized around both nuclei. And so that's the difference between atomic orbitals and molecular orbitals. The molecular orbitals show the molecule being held together by the electrons. The atoms are actually held together by the electrons. And so quite often, atomic orbitals are used to sort of approximate molecular orbitals, just as what is happening here. It will be important for you to be able to look at a structure and recognize whether atomic orbitals or molecular orbitals are being used to depict the molecule. The atomic orbitals are localized around their own nuclei. So that will be easy to differentiate. Molecular orbital theory, as I said, when the atomic orbitals come close together, they will overlap, they will form a bonding molecular orbital and an anti-bonding molecular orbital. And here is the node that I mentioned before. You can see this is a stabilizing interaction. The one electron in a 1s orbital and a second electron in another 1s orbital, so these are two different atoms, are coming together and they're becoming paired and they are populating a bonding molecular orbital, so they're going down in energy. And the amount of energy that this orbital, the bonding molecular orbital, is below the atomic 1s orbitals is equivalent to the energy that the anti-bonding molecular orbital has been raised. So this energy is equivalent to that energy. And the anti-bonding molecular orbital is not populated. Populating the anti-bonding orbital will cause this corresponding bonding molecular orbital, or this corresponding bond, to break. Each bonding molecular orbital will have a corresponding anti-bonding molecular orbital, and if you want to break this bond, you populate that, the anti-bonding orbital. Once again, this is the anti-bonding MO, and this is a bonding molecular orbital. This is for CH3Br. CH3Br. There's a lot of areas of atomic orbital overlap here. Each molecular orbital can hold 2 electrons. In the ground state, electrons occupy a lower energy molecular orbital, and the higher ones, which are anti-bonding, you can see the anti-bonding node here, remain unoccupied. So we do pay quite a bit of attention to the highest occupied molecular orbital, and we pay attention to the lowest unoccupied molecular orbital. These are the ones that are used in the chemical reaction. Now, we must hybridize the atomic orbitals, in particular, especially for carbon. So carbon, remember, has the 1s orbital occupied and the 2s orbital occupied, and it also has one electron in each of the 2p electrons. However, we know that carbon bonds in a manner such that each of its bonds points out in a separate direction in a way so that these bonds are as far apart as possible. This makes sense because each bond has 2 electrons. The electrons are negatively charged, and so they will move in order, or occupy space, in order to be as far apart as possible because they're negatively charged and electrons repel each other. And so even if one excites one of the electrons in the 2s orbital, here we're just considering the valence electrons. We're not considering the electrons in the inner shell. We're just going to look at the valence electrons, just these 4 electrons in the outermost shell. And so even if one populates that up to a 2p orbital, this still does not explain the directionality of these 4 bonds, because while these 4 bonds are equivalent, these 4 electrons are not. And so a different operation needs to be taken in order to make these 4 electrons and these 4 orbitals equivalent. And so what happens is these, again, we're not going to consider the 1s orbitals because those are in an inner sphere. They are not valence electrons. So let's just look at the valence electrons. These 4 electrons are the valence electrons, and so what happens is they hybridize into 4 degenerate orbitals, and that means of equal energy, and these are called sp3 hybridized orbitals. They're called that because they are 1 part s and 3 parts p, and you can see that sp3. And if you look at the energy of these orbitals, you'll see that they are 3/4 of the way up from the level of the s orbital and 1/4 of the way down from the energy level of the 2p orbitals. So they are energetically, they do reflect the fact that they are derived from an s orbital and 3p orbitals. They have that energy. So they are 1 part s and 3 parts p. You can think of them that way. And their shape is a little bit different also. We'll go into that quite a bit later. So the next one is the hybridization that's necessary for ethene, or sometimes called ethylene, and that hybridization is sp2. In sp2, you can see the angles HCC or HCH. They're around 120 degrees. And so we need to have hybridization that will allow those sorts of bond angles. And also, all of these atoms are planar. So we have a p orbital. This p orbital part on each carbon participates in a pi bond, which is represented by the second line here between the two carbons. So these two carbons have a double bond, one sigma bond and one pi bond. So we've got 1, 2, 3 sigma bonds for this carbon, and 1, 2, 3 sigma bonds for this carbon. So those sigma bonds are pointing more or less away from each other. Once again, they are have electrons in them, and those electrons will those bonds will arrange themselves so that they are as far apart from each other as possible, because electrons repel each other. They are negatively charged. And so we must, once again, hybridize the valence electrons, although not all of them. Here we have 1, 2, 3 of the bonds that are hybridized. That's 6 electrons. And so we're going to take 3 of those, of course, from carbon, and then 1, 2, the other 3 will come from the other atoms that are in these bonds. But it's the carbon, the central atom, that is hybridizing. And so here, this time, we're hybridizing the electron that's in the 2s orbital and electrons in 2 of the p orbital. One of the p orbitals is a spectator. It's not participating. It's the other 3 orbitals, 1, 2, 3, that are hybridizing, and these will be, each of them will be 1 part S and 2 parts P. Hence, they are called sp2 hybridized. And the energy level will be 2/3 of the way up from the 2s level and 1/3 of the way down from the 2p level. So the energy level of these hybridized orbitals reflects the fact that each sp2 hybridized orbital is 1 part s and 2 parts p. And then, as shown here, each of those orbitals is populated by 1 electron from carbon. Now, this right now is not showing a bonding situation. So the second electron will come into each of these orbitals once the carbon is bonded. This is showing an unbonded carbon, a carbon that is isolated. This is showing the orbitals of that lone carbon. So here is the p orbital. Here are the 3 sp2 hybridized orbitals. They are pointing away from each other, because when each of these is occupied by 2 electrons, they will take a position in space such that they are as far apart from each other as possible. And so these 3 are coplanar. They are lying in one plane. And so in order to be as far apart from each other as possible, the angle between these orbitals will be 120 degrees, 120 degrees, 120 degrees. So 3 times 120 is 360. And so that accounts for all of the angles in that plane. The p orbital is not hybridized. The p orbital is orthogonal or perpendicular to the plane created by these other sp2 hybridized orbitals. Now this shows a bonding situation. So this molecule is ethane. You can see the hydrogens, hydrogen, 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 hydrogen. So this is C2H4. So this shows the smallest alkene. And so here you have the 2 sp2 hybridized orbitals, one coming from one carbon and the other one coming from the other carbon. They have moved in. Each one donates a single electron to form a 2-electron bond, and this is totally normal. I might point out in each of these, if you look carefully, you can see the back lobes. Here is the back lobe for this orbital. Here is the back lobe for that orbital. This orbital has a back lobe, and this orbital has a back lobe. It's a little bit difficult to see, but they are there, which is good. So also, when hydrogen comes in, the hydrogen donates 1 electron, and this sp2 hybridized orbital has an electron coming from carbon, and that's 2 electrons in this CH bond. Similarly, this hydrogen will donate 1 electron to that bond, and carbon will donate 1 electron to this CH bond, and that electron from carbon will be in an sp2 hybridized orbital. So these are sigma bonds, these are sigma bonds. And it's the exact same situation down here on this carbon. Carbon is donating 1 electron, a hydrogen is donating 1 electron. This is a sigma bond also. Notice in the sigma bonds, you have this end-on overlap where the orbitals are coming in and overlapping in an end-on manner. So that takes care of the sigma system in ethylene or ethene. Those are 2 names for the same molecule. We also have the pi system. So one carbon has this atomic orbital, the other carbon has this p atomic orbital. They are exactly alike. Each one is going to donate an electron to this pi bond that will now have 2 electrons. So this is an atomic orbital representation or approximation for a molecular orbital. This is representing a molecular orbital, but it's doing it using atomic orbitals. And that's good in this case because it's showing where the electrons come from and how the molecular orbitals form. I might point out that these pi bonds are formed from the interaction of 2 p orbitals in a sideways manner. So the p orbitals are interacting sideways, above and below the plane, so that they will form a pi cloud above and below the plane, and both of those pi clouds are part of 1 pi bond. There's a node in here at carbon at the nucleus. And also, if I might just say now, if you twist one end so that the p orbital is pointing out at us and this p orbital is going up and down, so if these are twisted, they're no longer overlapping, and that will destroy the bond. It is necessary that the 2 p orbitals be parallel in order to have a bond. This can be twisted a little bit maybe 30 degrees out of the plane. The more it's twisted, the more the bond is destroyed. So here, it's a side-by-side overlap here in the pi system. The electron density is spread out above and below the plane. If you add together the part above and below the plane, that is one pi bond. Pi bonds are weaker than the sigma bonds because the pi bonds, the electron density, is farther away from the nuclei. In the sigma system, the sigma bonds lie close in to the nuclei, and so they are more stable. So now, let's look at this. Here is a molecular orbital. Do you see how this orbital is going across? It is delocalized across both nuclei. So this is a molecular orbital. Above and below the plane, that's one orbital if you add together the part above and below the plane. And this is called a bonding molecular orbital because when it's populated, you can see when this is occupied, it actually shows you how the two nuclei are held together. When electron density is residing in this bonding molecular orbital, the two nuclei are held together. That's why it's called a bonding molecular orbital. Look up here at the antibonding orbital with the node. If this is populated, you can see that there is no interaction here, no overlap. Okay, and so this will not contribute to the bond between these two atoms. As a matter of fact, if one populates this antibonding orbital, and that bonding orbital correspond to each other. Every time you make a bonding orbital, an antibonding orbital is created, and they form a pair. This antibonding orbital corresponds to this bonding orbital. If you populate this antibonding orbital, it will tend to, or it will, break the bonding orbital or the bond that it corresponds to. So this is a set. This is a pair. Okay, this antibonding orbital doesn't correspond to some other bond. It corresponds to this bond. Now we have ethine. So sometimes it's called acetylene. This is sp hybridization, in which it's a linear structure. In order to form a linear structure, one needs to have orbitals on carbon that are equal and as far apart from each other as possible. And so in order to create that, we're going to hybridize the 2s orbital and one of the p orbitals. And when that happens, this will be an sp orbital. Even without the electrons, it's still an sp orbital. These electrons are occupying the sp orbital. And so the energy of this sp orbital, it is, because the sp orbital is half s and half p, the energy of the sp orbital will be exactly halfway between the s and the p orbital. Okay? Now we're only going to consider the valence electrons again. The 1s electrons are not important. And so we've got the 2sp hybridized orbital and these two spectator orbitals that do not participate, and these two orbitals are p orbitals. Each one can participate in a pi bond, and so that gives rise to these two pi bonds on acetylene. And this shows you the atomic orbital representation of the molecule. So once again, hydrogen and carbon have formed a bond. Notice how this sp hybridized orbital lies farther out than the s orbital. Okay, so carbon is using an sp hybridized orbital. Hydrogen is using its only orbital it has, the s orbital. Each of these atoms is contributing one electron, and this is forming a sigma bond. Now we have the bond between carbon. This is the overlap of two sp hybridized orbitals. Each carbon is contributing one electron to that molecular orbital. That is an atomic orbital representation of a molecular orbital. Here, once again, hydrogen is contributing one electron and carbon is contributing one electron to this bond. Then you have p orbitals. The p orbitals here, the top lobe and the bottom lobe, that's one p orbital. Now you have the top lobe and the bottom lobe, that's another p orbital. Then you have the lobe coming out at you and the other lobe going back behind the screen. This is another p orbital, and here this is another p orbital. Once again, you have the sideways overlap of the p orbitals, and then here the sideways overlap of these two p orbitals. So this is one pi bond, this is the other pi bond shown in acetylene. So the two carbons have three bonds connecting them. They have a sigma bond, the pi bond lying in the plane of the screen, and the pi bond that is perpendicular to the plane of the screen. So here we have the three structures side by side. This is ethane, ethylene, ethine, or acetylene, having a single bond, a double bond, a triple bond, as you would expect when the two atoms are held together by a single bond. That bond length is longer than if they're held together by two bonds. So the bond length gets shorter, and then it gets even shorter when there are three bonds between those two atoms. That's exactly what you would expect, and that trend is exactly what happens. The bond energy of a double bond is higher than that of a single bond, and the bond energy of a triple bond is still higher. So this is exactly what would be expected. Valence shell electron repulsion theory, VSEPR. So valence electrons, as I pointed out, there are 4 of those on each carbon. Whether they are shared or lone pairs, repel each other. So look at this. You have 4 pairs of electrons surrounding carbon. Remember, we talk about the stability of the field octet. So here, carbon has the stability of the field octet. So that's 1, 2, 3, 4 electron pairs. So here, this is said to have a steric number of 4. These 4 electron pairs will occupy space in a manner to be as far apart from each other as possible. Now we have NH3. Each NH bond has a pair of electrons in it, and we have 1 lone pair. So you simply count up the pairs of electrons, whether they are bonding or non-bonding, and the answer is 4. So the steric number here is 4. Similarly, with oxygen, each OH bond has a pair of electrons in it, and then oxygen has 2 lone pairs. So if you count up the number of lone pairs, 1, 2, 3, 4, this oxygen has a steric number of 4. If the steric number is 4, then the molecule has sp3 hybridization. If it is 3, then the molecule, the central atom in that molecule, has sp2 hybridization. And if it is 2, then the hybridization is sp. So here you can see examples. Methane has 4 equivalent bonds, and they are each pointing in opposite directions, and so they are spread out as far as they can get from each other because of the electron repulsion in the bonds. You'll also have electron repulsion between the bonds and the lone pairs. And so here, the pairs of electrons will also spread out. And so this is still surrounded by 8 electrons, and this is still surrounded by 8 electrons. Notice that here the lone pair occupies a lot of space. Here this is longer and thinner, and so these 3 bonds, the hydrogen, nitrogen, hydrogen angle is 107 as compared to 109.5. And then down in water, the HOH bond angle is compressed even farther because these lone pairs occupy more space. You can think of it as they are shorter and fatter than the electron density in an actual bond. And so that forces the bonds to hydrogen to be closer together. Now let's look at some other molecular shapes. So we just finished looking at these 3 molecules, and we saw that the steric number in each one is 4, and so it's tetrahedral, tetrahedral. Here, this is trigonal pyramidal if you are just considering the atoms themselves, and here if you're just considering the atoms themselves and not the lone pairs, then this is bent. Now let's look at 2 other molecules. We're going to look at BF3, where this is different. This is different because boron has an empty p orbital coming out of the plane of the spring. And so this plane is, this empty p orbital, the orbital is there, but it's just not filled. And so it is unlike in H3 because here we have a pair of electrons. BF3 does not have this pair of electrons. Here the pair of electrons is pushing these bonds closer together, and so that they can move away from that pair of electrons, and so it makes these angles smaller. And that doesn't happen with BF3. And so here these now can move as far away from each other as possible. And so that's going to be 120-degree angles. The boron-fluorine angle is 120 degrees because these bonds, the electrons in these bonds, do not have to move away from electrons in a non-bonding orbital. And so this is sp3 hybridization. The boron is sp3 hybridized, and the steric number is 3, trigonal planar. When we talk about the shape of the molecule, we're not considering the lone pairs. We only consider the atoms. Now, let's consider beryllium hydride. The beryllium hydride has a linear geometry. So the steric number is 2. The steric number is 2. You only have 2 pairs of electrons on beryllium. Both of these bonds are to hydrogen. And so the electron pairs will move as far away from each other as possible. And so the angle will be 180 degrees. The hybridization to achieve this linear geometry of the atoms is SP. And so I'll let you draw a Lewis structure for carbon dioxide. So you'll need to pay attention to the sigma system and the pi system. There will be pi bonds here. Now, let's sort of review these molecular geometries. Remember, the molecular geometries, when we talk about the molecular geometries, we're just talking about the atoms. The lone pairs are not drawn. And so, for CH4, the molecular geometry is tetrahedral. For ammonia, even though you have a lone pair, the molecular geometry is trigonal pyramidal, okay? The lone pair is ignored. Here for water, we have two lone pairs, but those are ignored in naming the molecular geometry. So this is simply called bent. These three have a steric number of 4. If the steric number is 3, then the hybridization is sp2. Trigonal planar arrangement of electron pairs. If there is one lone pair, then the molecular geometry will be bent. If there is no lone pair, then the molecular geometry will be trigonal planar. If the steric number is 2, then the central atom is sp hybridized, and you'll have a linear arrangement of electron pairs around that central atom. And here we will describe the molecular geometry of this molecule by looking only at the atoms and not any electron pairs, and so this will be linear. So that summarizes the molecular geometry, and next we will go on to the final lecture of Chapter 1, which is a review of your general chemistry.